These are notes on atomic models, or how to make a model of the atom, and it's in your textbook in chapters 5.1 and 5.2. 5.1, you'll notice, is a recap of the development of the model of the atom. It builds on chapter 4 and all the stuff in there. This is the model you were taught either perhaps in middle school or earlier in high school, the Bohr model. And it should be very familiar to almost all of you, with a positive nucleus in the center and then rings or orbits going around the nucleus. And there are some problems with this model where it breaks down, and I'm going to talk about those in a few minutes, and we'll see what led to the necessity of the electron cloud model, which is a much more complete model, but a little more difficult to understand. The things you've been taught are that the electrons that are farther from the nucleus have more energy. Just like going up the stairs in your house, you have more energy compared to the nucleus, the ground floor. As you go up, you think about, say, potential energy increasing. And so electrons, as they go from the inner orbits to the outer orbits, need to absorb energy. Similarly, as they fall back down towards the nucleus, they're going to release that energy. And they're going to release that energy as light. And we're going to talk about that a little later this week. Electrons also fill their shells from the bottom upward. Think again like a house. You don't suddenly materialize on the third floor. You start on the ground floor and you work your way upward. Those two things are still absolutely true and hold when we get to the electron cloud model. What you learned, however, is that the first shell can hold 2 electrons, the second 8, the third 8, the fourth 18, etc. So you learned this sort of 2, 8, 8, 18, etc. There are a couple of problems with this, which some of you have picked up on already. The first problem is that you were taught that atoms can have no more than 8 valence electrons. A valence electron being the outermost electrons in an atom. So, and that's absolutely true. Electrons can have no more than 8 valence electrons. But if that's true, then how could the 4th level hold 18 electrons? It would seem then at that 4th level you could have up to 18 valence electrons if it can hold 18. So clearly something's wrong with this model, because the atom really does only have 8 valence electrons at most. A second problem is that the third energy level doesn't actually have 8 electrons. It holds 18 electrons. But it fills them in such a way that you can make a simplified model saying it only holds 8. And I'll show you that a little later. So this model is a great model to start with. It makes sense to people, but it only works up to element 20, which is calcium. The other problem with it is it gives people the impression that electrons are orbiting the nucleus like planets orbit the sun on some discrete path that is traceable, when in fact that is absolutely not true. And I'm going to show you a picture of the atomic orbitals, which are not orbits. An orbit is a circle or a path that an electron is following. That's an orbit around a nucleus. An orbital is a region of space. I know the words sound very similar, but they're very different. So let's take a look at these. So an orbital is a region of space where electrons are likely to be found. They're a region of space. I like to compare orbitals to classrooms. Classrooms are regions of space where students are likely to be found, but at any point in time, a student could be in the bathroom, or on their way to the bathroom, or on their way from the bathroom, or at a dentist appointment, or in the office. So while students during class time cluster in classrooms, you could definitely make the argument that that's where they're likely to be found. There's a greater probability of finding a student there. That's not necessarily where they are. So I'm going to show you a picture of the orbitals. Don't think that you need to draw all of these. I'm giving you a larger view than you actually need for the scope of this class. So these are the orbitals, and you can see there's clearly some sort of organization because they're organized by row and by color. Now obviously the color doesn't mean anything other than to help you organize them. But let's just look at this picture first before we name anything. We'll notice that on each diagram there's an X, Y, and Z axis. So remember, that makes it 3D. And on this diagram, the X and Y, of course, are perpendicular to each other, and they're kind of going into and out of the page. And then the Z-axis is going up and down. So that gives you a 3D view of these. The second thing to notice is, with the exception of this big red ball on top, these really are not circular orbits, and this big red ball is a sphere. Again, not of an orbit, but an orbital, a region of space where you're likely to find an electron. So let's give these some names. Some of you already know these names. Some of you can maybe figure it out based on looking at all of these diagrams. The first are called the s orbitals. And you can remember s because s and sphere start with the same letter. That is not to imply that S stands for sphere. It's just a helpful way to remember it. 2 electrons can fit inside any orbital. So for the s orbitals, that houses 2 electrons. The next row are the p orbitals. And I had a professor once who said that p, you can remember p because it's kind of shaped like a peanut, in that, you know, you've got these 2 lobes. There are 3 p orbitals. Each orbital, as I just said, holds 2 electrons. So 3 times 2 are 6 electrons. You can have 6 electrons in the p orbitals. And you'll notice that each of the p orbitals is on one of the 3 axes. So if you were to superimpose these 3 axes on one another, and you can find some websites if you're interested that will superimpose them for you, you get a sense of what a full p orbital or p shell would look like. The next orbitals are called the d orbitals. I don't know what d stands. I mean, there's no helpful way to remember d. You'll notice there are 5 d orbitals. Each orbital holds 2 electrons, so 5 times 2 is 10. And on the bottom we have the f orbitals. There are 7 f orbitals. Each orbital holds 2 electrons. 7 times 2 is 14. The only shapes that I'm ever going to expect you to know are the s orbitals and the p orbitals. But we are going to do some work with the d, and we'll touch on the f, so it's helpful for you to know they're there, but as far as remembering the shape, don't worry about it. As I said, if you are interested, there are some pretty neat websites where they will superimpose the axes on one another, and so you can see how these all fit together. And it's pretty neat. It's kind of like a puzzle. So let's look at how we're going to fill the orbits. So there's a couple things. Before I give you any rules or anything like that, let's again just look at this diagram. This is a helpful diagram for you to use when filling orbits. You'll notice that energy is increasing from the bottom up. So if you go back to your Bohr model, the nucleus would be on the bottom of this diagram below the blue box that says 1s. Now, just like we numbered the orbits that were around the nucleus, we give each energy level what's called a principal number. And we call that principal number n. So, for example, the blue box, there's only one, that's the first principal energy level, and that we would say is n equals 1. So you can think about that as those would be those dots. If you want to bring this back to Bohr, those would be those electrons in that first orbit. All of the red boxes then, whether they're s or p, are n equals 2. And again, go back to Bohr, it goes 2 and then 8. These are the 8 electrons that would be on the second one. But what's interesting about the second energy level, and obviously with the third and fourth and so forth, is that the 2s electrons are actually at a slightly lower energy than the 2p electrons. They're all the second energy level, n equals 2, but some of the electrons are actually at a slightly lower energy than others of the electrons. So within any principal energy level, except n equals 1, you can have several types of orbitals. These green ones then are n equals 3, all of them, the 3s, the 3p, and the 3d. I don't have enough space to put an n equals 4 arrow in, but obviously the fourth, the yellow boxes, would be n equals 4, and so forth. Now, if you notice, go back to where, we talked about the n equals 2 would be the 8 electrons on the second ring. You'll notice on the n equals 3, the 3s and the 3p electrons are pretty close together as far as energy. And then the 3d, there's a bigger jump, and in fact, if you look carefully, the 4s electrons are actually lower energy than the 3d electrons. Those electrons actually fill before the 3d, which is why your middle school teachers could say it goes 2, 8, 8, because they know that as long as we break the model at calcium, which is atomic number 20, which would fill up the 4s, you're never going to hit those 3d electrons. So that's why I said earlier that third ring actually holds 18. But the way it fills, if you manipulate which elements you give your students, you'll never know that it holds more than 8. So that's how you can kind of reconcile those two models. So, a couple of rules about filling the orbitals. You're going to fill orbitals from the bottom, which again is the lowest energy, upward. That's known as the off-Bohr principle, where it's going to go lowest energy and higher. As we've already said, the 1s orbital is closest to the nucleus and therefore has the least amount of energy. Each colored box can hold 2 electrons. Earlier, when I showed you all of the orbital pictures, we said that each orbital could hold 2 electrons. So each one of these boxes is 1 orbital. And so, for example, on the p, there are 3p orbitals, so that's why there's 3 colored boxes in the 2p, the 3p, and the 4p. There are 5d orbitals, that's why for the 3d there's 5 boxes. And that idea that each colored box, or each orbital, can hold 2 electrons is known as the Pauli exclusion principle. Finally, at one level, like say the 2p level, you would put 1 electron in each box before doubling up. And that's known as Hund's rule. And I'm going to show you how that works with an example on the next slide. One of the things to notice is this diagram only goes up to 4p. Obviously there are more orbitals, and I'm going to show you those. This diagram doesn't even touch the f orbitals, but we don't need it for the atoms I'm going to show you, and this makes it a little easier rather than having a ton of boxes everywhere. And then, as we talked about, due to the way the electrons are configured and the energy, average energy of the shell, of the orbital, the 4s level actually fills before the 3d level. And that's the only exception on this diagram. I'm going to show you how you can figure out how each orbital fills, because it doesn't necessarily go in order. So let's take an example. Let's look at sodium. Sodium has 11 electrons when neutral. And so I want you to try to go ahead, use the Pauli exclusion principle, the off-Bohr rule, the off-Bohr principle, and Hund's rule, and you try to fill in the electrons. And then I'm going to show you how I would fill them in. Okay, I'm going to fill them in using weird white ovals because that's what worked for PowerPoint. If you look in your book on page 134, you'll notice that they actually use arrows. Arrows are absolutely the standard to use. Nobody uses weird white ovals unless they're making a PowerPoint, and that's what they happen to use. So I would like you in your notes to use arrows, or in your homework or on tests, use arrows. Okay, so this is how I'm going to fill my orbitals. I'm going to start with the 1s orbital. I know I have 11 electrons to fill. So 2 electrons go in that 1s orbital. So, okay, 11 minus 2 is 9. I have 9 to go. So now I'm going to move up to the 2s orbital. So 2 electrons fit in the 2s orbital. So that's 2 plus 2 is 4. I have 5 left. Here's where I use the Pauli exclusion principle. I now have, what did I say, 5, wait, 2 plus 2 is 4. No, I'm sorry. I have 7 electrons left. Bad mental math. So I'm going to fill 1 in each of those 2p orbitals. Then I'm going to go through and fill the second. Now, if you're better at mental math than I clearly am, and you could say, okay, I know I'm going to fill up the 2p's, that's fine if you filled them up, but if, say, we were using an element such as oxygen that's going to end in those 2p's, you'd want to make sure that you're filling 1 at a time before doubling up. So now I'm at 10, and now I can go up 1 more, and that's my 11 electrons. So I've got 2 electrons in the 1s, 2 in the 2s, 6 in the 2p, and 1 in the 3s. If you want to talk about valence electrons, the valence electrons are the electrons in the highest principal energy level. So those would be those 3s electrons. Now, when we talk about those valence electrons, let's say we had an element that filled up to the 4s, even though we hadn't filled, or let's say we got them that filled up to the 3d. So we fill the 4s and then the 3d. Our valence electrons are the ones in the highest principal energy level. So even though there would be electrons in the 3d, those 4s electrons would still be your valence electrons. We'll talk about that a little more in class. Expect a warm-up question on it. So then the way we write this is we write 1s2, where 1 is the principal energy level, that n number, n equals 1, s is the orbital, 2 is the number of electrons in it. So we say 1s2, 2s2, 2p6, 3s1. Or we can actually abbreviate that to neon in brackets. If you look at your periodic table, neon is the previous noble gas, and noble gases always fill up a principal level, and or always have, let's say this, always have 8 valence electrons, which is the maximum number. And so we can always go back to the previous noble gas and then just add on from there. So neon is 1s2, 2s2, 2p6. So that's abbreviating that to Ne. So here's a helpful diagram rather than having all these clunky boxes. It's an upside down diagram from the previous one. So instead of 1s being on the bottom, 1s is on the top, and the energy is increasing as you go down. But if you go to make this diagram, say on a test, if you want to make kind of a diagram for yourself, you'll notice if you go horizontally across, it's the orbitals that are associated with that principal energy level. So 1s, and then it goes 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and so forth. So one of the things that this third bullet says is that in order to make this diagram, you do need to remember how many orbitals are at each level, and then you also need to remember that each orbital can hold 2 electrons. And then you kind of put in these diagonal arrows. And those diagonal arrows then are the order in which you fill the orbitals. So 1s goes first, then 2s, then 2p, 3s, then 3p, and here's where you get 4s, and then 3d, and then 4p, and then 5s, and then back to 4d. So it's crazy to try to remember this order. This is a really helpful diagram to help you reconstruct that, so you don't have to memorize this order. I'm also going to show you the way that you can just use the periodic table to make this work. So what I recommend you doing, because I'm going to go to the next slide, is make sure you copy this down so that then you can look back on your periodic table and this diagram together. So here are the orbital blocks on the periodic table, and that's why this works. Remember that the s orbitals only hold 2 electrons, so you'll notice the first 2 groups, that's known as the s block. And then, with the exception of helium, and we'll talk about why helium is over in the noble gases instead of over on top of beryllium. Then remember the p orbitals, There's 3 p orbitals. Each one can hold 2 electrons, so that's 6 electrons. Notice in the p block, that's 6 elements. And so now you're starting to see maybe why the periodic table is shaped the way it is. The d orbitals, remember there's 5 orbitals, they each hold 2, that's 10 electrons. If you count the d block in the middle, the transition metals, you'll notice that that's 10 elements across. And then the f orbitals, there's 7 of them, they each hold 2. If you go down to the lanthanide and actinide series, also called the inner transition metals, you'll notice those are 14, or 7 times 2 elements across. So the way you can figure it out, if we look at sodium, so find sodium, it's atomic number 11. If we start counting over, it would be, starting with hydrogen, that would be 1s1. And then going to helium, that's 1s2. Now we drop down. Notice the period is going to correspond loosely, at least with the s's, to the principal energy level. It doesn't work as well for the d's, but it does work for the s's. So then lithium would be 2s1, beryllium 2s2. And now we jump in boron's the next, that's in the p block. So that's 2p1, 2p2, 2p3, all the way over to neon, which would be 2p6. Now, don't think neon is only 2p6. Neon is, because it's got all the electrons that came before it, so it would be 1s2, 2s2, 2p6. Now go over to sodium, 3s1. So that's how, even better than that diagram I just showed you, you can actually use the periodic table to understand in what order these orbitals go. And that's why those transition metals don't come in until after the 4s electrons. Then we get the transition metals, those 3 Ds. Here are some citations, which are just good to have, but they'll also give you some more information, as will your book. I highly recommend your book. I cannot say this enough. Use your textbook. If you have questions, please add them to the comments of this video, or please ask them in class.